Okay, Assalamualaikum and good afternoon, everyone. So welcome back to another seminar of the department. So this is for the month of September. So today we will have Dr. Tan Sin T to give a talk. Dr. Tan Sin T is a senior lecturer at our department in UPM. She joined in July 2018. Previously, she was as a postdoc at Nanyang Technological University and in UKM previously. I think probably she did her PhD, is it? And then she is an experienced researcher, manages a portfolio of training courses offered to researchers and industry players from government and private sectors. She is a reviewer and editorial board member in a high-impact journal, and also an alumni in the Lindau Nobel Laureate Network, and a member of MES. Her research interest is in the field of nanomaterial design and nanotechnology, and she has received several government research grants in the area of advanced materials research. And she has been involved in consultation work for private organizations, and she has scores of publications in high-impact journals. I think without further ado, Dr. Tan, are you ready for your presentation? Hello?
Hello.
Okay.
Can Dr. Hisham hear my voice?
Yeah, sure.
Okay. Yeah, thanks Dr. Hisham for a very nice introductions. And thanks again for inviting me this is my second time, to join the seminar of Jabatan Physics Faculty Science UPM. And thanks again for giving me this chance to present my works. Okay, so today I will going to present a little bit about my previous study and also some of the findings that we get it in the previous years and also latest. Okay, so the title for today for my presentation is Emerging Nanomaterials for Advanced Optoelectronic Application. Yeah. So my presentation for today will cover the 7 part, which is not limited to some of the general idea of the nanomaterials, and then we will focus back to specific applications, how we can utilize and modify the nanomaterial and use it in application of sensors, solar cell, energy storage devices. Bifunctional devices is mean that we can use one nanomaterial and apply to different kind of the applications, and some of the take-home message and also the acknowledgement to my collaborators. Okay, so everyone can actually stop me, if you have a question in any of the slide of my presentation. So first of all, I want to thanks to the generations of the nanomaterials. Because of nanomaterial, actually we are very convenient for today's household and also some of the issues that we are facing right now, like the COVID pandemics. So everyone might know that in COVID pandemic, the vaccinations, the brand like Sinovac, Pfizer, all of them are using a different kind of nanotechnology to cure and giving not cure but giving improve the immune system of the human body. For example, Pfizer is using a mRNA. So mRNA is a type 2 generations of the nanostructure, which called as an active nanostructure. So they're using a liposomes nanoparticles to actually attack to some of the protein spike in our if you are getting infected with the COVID-19 virus. So here I want to talk a little bit about the generations of the nanomaterials. So roughly there is 4 generations of the yes.
Are you using a mic?
Yeah, I'm using the mic. Is it?
Maybe can you sort of don't be too near the mics, because I think there's some noises.
Okay, how about like this? Is it okay?
Nearer a little bit.
Like this, okay?
That's better.
That's better, yeah.
Okay.
Okay, so sorry about some of the technical issue here. Okay, so there is a four generations of the nanomaterials. Okay, which the first generation is actually we can consider as starting at 2000 years before, and we know it as a passive nanostructure. So in the field of the passive nanostructure, people are tends to just designing, okay, a different type of the nanostructure, for example, like the disperse and contact nanostructure, like the colloidal particle that you see from the images here. Okay, so they are using some of the ligand material to self-assemble the nanoparticles and make it to use it in different kind of the applications. So some others product incorporating nanostructure like the nanoparticle and reinforced material is also grouping in the first generation. I think most of us is working on this by just designing, okay, the how the arrangement of the monodisperse particle. And then up to the years of the 2005, people is starting to working on the active nanostructure. This is called it as a second generations of the nanomaterial design. So in the second generation of the nanomaterial design, they are working more toward the bioactive nanostructure like the targeted drug nanoparticle that is utilized up to today. So the images here is actually showing you some of the metal nanoparticles. Okay, so people is using a ligand, okay, to modify and functionalize the metal nanoparticle and make it to the control of the cancer cell treatment. Okay, and also getting SNA amplifier and additive structure materials that having a physical chemical active site is also considered in the active nanostructure. So when coming to the years of the 2010s, okay, so the scientist is starting to working in the system rather than just design the nanostructure. So in the third generation, they are focusing in the system of the nanosystem. So they are trying to making a new hierarchical architecture and try to assemble the nanostructure into a 3D networking. So the example here is showing some of the metallic nanowire that is formed from the microbial organism. So what they want to do is they are mimicking, okay, the bacterials or any of the bacterial system, okay, together into the nanostructure and making a nanostructure growth and able to use in the not only in the nanotechnologies but also in the biotechnologies. Okay, so in the years of the 2020, okay, which is a recent year, so this is also the latest generations of the nanomaterial design. So people is working on the molecular nanosystem. So I think there is quite a lot of the scientists here is heard about the MorphCorp, which is a metal organic framework, and also the covalent organic framework. So what the scientists doing in the Morph and the Corp design is they can actually placing and design whatever kind of the material with the property that they are needed, okay, for certain type of the application. So for example, like Morph, we can actually choosing or select the magnetic carrier or the ligand that you can use to modify what kind of the framework structure that you need in the molecular system. Okay, so this is some of the short introduction, but all kind of the nanomaterial that need certain of the synthesis method to initiate, okay, the process. Yeah, so the general process using by the scientists up to today is a hydrothermal synthesis method. So in short, we can say that the hydrothermal synthesis is you're forming some of the nanostructure from the hydro, is mean from the water medium, and you apply certain of the heat to activate the nucleation process of the system. So why this method is come very facile and very convenient is because it's always just needed a very low cost and not environmental dependent too much. So if you look at the images at the bottom right, okay, bottom right, so you can actually observe that the system is actually called as a conventional oven. So people is normally using a Teflon lined container to preserve the pressure during the growth system. Okay, so another type of the common method people using is called as a mini emulsion colloidal method. So mini emulsion colloidal method is come very active basically starting from the years of the 2000, okay, where they are starting to working in terms of the field of the photonic crystal, and it is needed for them to have a very well dispersed of nanoparticle. So they were trying to use a different kind of the ligand, which is maybe in terms of the hydrophilic and hydrophobicity of the properties to control the arrangement of the nanoparticle. And some people also using in term of the ceramic synthesis, like the cold precipitation method. Okay, this is a quite common. And the mini emulsions colloidal method is also very convenient because it can operating under the room temperature and always having a very high purity system that you can obtain from it. So this is some of the images that we are trying to extract from whatever we done in our research group. Okay, so this is the example showing here is most of the metal oxide that is successful design from our research group. So in here I have split it up to the four part. The first top left hand side part is actually the zinc oxide nanostructure, which is quite common use in most of the optoelectronic devices. So we are trying to modify the surface of the zinc oxide by using a different kinds of the surfactants and material. And from here, we successfully to tune the nanostructure for even the one-dimensional to the three-dimensional structure. Like what you can see here, it is actually changing from a nanoplate is able to change to the three-dimensional, a very nice nanoflower. Okay, and then on your right hand side, okay, the top images here is actually showing some of the metal dot zinc oxide nanostructure, which we are putting some of the metal nanoparticle into the zinc oxide precursors to altering the inherent the electrical optical property of the system. Okay, so in here we also successful to turn the mesoporous nanoparticles film, okay, toward a very high surface area of the nanoflower, which is appear in the 3D dimension. Okay, on your left hand side bottom is actually a quite common things that you can actually found out in the literature review. We also doing this by just applying some of a little bit doping to the zinc oxide nano without changing the structure, but just changing the electricals or optical property of the system. Okay, but the structure will still remain as a nanorod. And last but not least, in your left bottom corner of the image is showing you some of the TiO2 nanorod. So our group is focusing sometimes in the TiO2 nanorod is because we are working in the photocatalysis. Okay, or some of you might out of this field, it is something like we clean the water. Okay, we clean the water using the catalysis. So in catalysis, the standard material that we're using is a TiO2 P25 degusser. So our group is also changing from the degusser nanoparticle and make it to the one-dimensional structure by altering the defect of the active site, which is on the O2 plane. Okay, so other than that, in the latest, so we have starting to working and moving toward to the two-dimensional structure of the molybdenum disulfate. Okay, so and here is showing you some of the images of molybdenum disulfate that we have obtained, and we have found that molybdenum disulfate that we found from the convenience conventional way is having a thickness which is very thick, about a 27 nanometer, and is combined between the multi-layer and the single layer of the molybdenum sulfate. After that, we have conducted some of the analytical analysis using a Raman analysis, and we have found out that our molybdenum sulfate dominantly appear in a multi-layer lah. So which you can actually see it from one of the Raman stretchings. Okay, the peak at about 4,003 nanometers. Okay, and also which is present by the A1G. Okay, A1G is actually the vertical stretching mode from the MO to the S. Okay, whereas we also detect the single layer of the MOS2 exists in our sample, which we detect the peak about 373 nanometer come from the horizontal stretching mode of the MOS. Okay, so other than that, we also trying our best to come out another new type of nanomaterial called as a manganese oxide. Okay, manganese oxide that we produce in our lab is we are more utilizing much in the flexible devices. So our aim is come out with the flexible nanostructure. So the MnO2 that formed from our lab is always flexible and have a micrometer long range with the diameter of 15 to 30 nanometer. So from here, we're also using a Raman analysis to study the stretching bond of the MnO toward its primary group of the MnO6 bond. Okay, so what we can actually observe from here is we get a very well crystallized MnO2, okay, structure. So, and just now is a little bit introduction about some of the nanomaterial that we have actually get it from our research team. And now let me give you some introduction how we can do the material selection and make use of this kind of nanomaterial into the different kind of the application. So there are the 6 common criteria is normally we are looking for. The first one is the wettability issue. So in the wettability issue, in short, we can say that it's something like whether your material you like the water molecule or don't like the water molecule. So what you can see from here is the wettability is kind of very important, especially for the solar cell approach and also the photocatalysis approach. Okay, for solar cell approach, give you an example. So if you have the material with a very poor wettability, okay, with a very poor wettability, we call it as maybe very hydrophilic. Okay, very hydrophilic. Actually, it is not really good. Okay, for the solar cell approach because we are intended to cause all our active material to infiltrate in between it. So basically, we want to have a little bit of the hydrophobicity. Okay, so this actually some of the bottom result is showing you some of the material with the poor wettability and good wettability. So like battery like or supercapacitor like devices, they are more preferred to have a good wettability. Okay, good wettability in terms of the hydrophilicity because all your electrolyte is dissolved, okay, inside to the water medium. So the good wettability of the hydrophilicity can actually improve the interface in contact between your electrolyte to your active material. Thus, it can improve a more better surface for the charge transfer rate. Okay, so the second one we are looking for is called as a surface area. So surface area here is commonly people have come to the misunderstood about the surface area for the surface active area or the total area of the nanostructure. So surface area that we are referring here is more to the active site surface area. So active site surface area you could actually see like for example in the zinc oxide nanorod you could have a top surface and the edge surface, but the only one that is improve your devices especially in the solar cell is only a top surface. Okay, but the side surface doesn't help it much. Okay, so in order for us to improve the surface area, we will actually just focusing to how can we functionalize our material to just improve the top surface of our O2 surface. Okay, and then the third one we are looking for is a conductivity. We will always measure the conductivities, electrical conductivity here I mentioned, so of the system, because if one of the system having a high electrical conductivity, we can actually further improve the charge density, okay, in the optoelectronic devices. Fourth is going to the long cycle stability. This one is for us to maintain a good cycle stability and also high capacitor retention in the supercapacitor devices. And the fifth one will be the morphology, which is focusing more to the pore size, distribution, and some of the particle dimensions. Okay, and last but not least is go beyond the thermodynamic stability because we can actually operate our system when apply the heat to the system, so we can actually have a stable in terms of the device rather than it's undergo the degradation. So from the nanofabrication to the application, there is a few of the property that we are looking for, which is not limited to the optical, electrical, and structural property. So this is how we are going to make a change and going to make a decision how we can alter our nanostructure into the different structure that is able to fit to any of the application here. So this is some of the applications that we're working in our lab, which is initiated from the optical gas sensor. Actually, this is my project that I initiated during my undergraduate. Okay, so and after that, we are moving a little bit toward the photo detector, solar cell photocatalysis, and energy storage devices, which is a supercapacitor. So now let me move on to the first applications in our lab. So this optical gas sensor is actually events on, we can say that I'm starting to involve it when I'm undergraduate, okay, and it is guided by one of my supervisor, Prof. Muhammad Yahya. So at the times, we starting to do two kind of the sensors, okay, during my degree and also my postgraduate study, and then we start to do two type of the pathway of the detection. One is a photoluminescent detection, another one is a absorbance detection. So why we choose these two kind of the detection is because the detection is extremely fast as compared to the electrical signal. So for the photoluminescent Center, we are actually starting the detection after the reaction by looking at the PL quenching, because during the reactions, okay, the electrons, when we excite our material with certain of the appropriate UV sensor, okay, so the electron will basically excite from the valence band to the conduction band of your semiconductor, and this electron will involve in the charge transfer, okay, during your isochrone is absorbed to the surface. Okay, for example, in the condition of the CO gas, so there is oxygen exists in the ambient, and this oxygen will first receive the electrons, okay, either from the conduction bands of your bulk semiconductor or from the surface defect that you have creating inside your emerging materials. Okay, so the isochrone will actually turn to the ozones, okay, and then they will react with the CO gas. So when they react with the CO gas, they will undergo the reduction and return the electron back to your system. And once the electron and hole is recombined, so you can actually detect the signal for the PL quenching. This process, it seems like 5 process is very long, but actually it just occurs in femto to the nanosecond, which is a very, very short time. So we have proceeded this experiment corroborate with the the Lim Coxen group. And then after that, we are trying to further modify our system to the adsorbance-based sensor. So in the adsorbance-based sensor, we get a more precise analysis by study the mechanism during the reaction. Okay, mean we are detect our material using the OAC method. OAC method here is a optical absorption correction method. We will actually consider before and after, and we take the differences between them. So from here we can see that we will evaluate the CO gas absorption during the air environment, and also what's the difference during a CO environment. And from here we get that after the CO environment, so the number of carrier in the conduction band is basically increasing and causing the energy band gap is increased. Okay, so this will actually altering the absorbance sensor very much. Okay, so this is some of the result that showing for our PL based sensor that we have conduct in a few couple years ago. So the top images here is actually showing you the detections, okay, the chamber that we are using it. So the nanostructure that we are doing it here is a zinc oxide nanorod. So we synthesis using a 2 different approach. One is a microwave, and we compare with the conventional hydrothermal method. So we found out that the microwave method is come out very fast reaction and is able to tune the surface defect is only on the surface at this side, which is a 002 of the zinc oxide, without altering too much to the crystallinity of the sample. So after that, we have found out that the sample A for the microwave is actually showing a better response as compared to those who are finding up the sample B in the hydrothermal synthesis method. So the microwave sample is giving us about the sensitivity roughly about 81% as compared to the sensitivity of the sample prepared for the hydrothermal is just a 44%. So the images for the PL here is showing you the sample, the localized measurement of sample in the PL, okay, or the PL during when the sample exposed to the air and the CO. So what can you observe here? There is a 2 region here. The first regions are highlighted by the bridge color here is showing you the UV region, ultraviolet region, while the second part is actually the visible region. So we can actually observe that our sample is become more active and responsive in the visible region. So he give a quenching, for example, this is a sample A which denoted by the line, the black color line and red color line. Okay, so you can observe that when the sample is exposed to the air, okay, this is a general PL spectrum, but when the sample is exposed to the CO gas sensing, so it will actually undergo a quenching. Why is quenching? Is because the electron, when he from the CO absorption, when he react with the oxygen, he will actually release one electron back to your conduction band and undergo the recombination. So this is why the quenching is occur. But when you refer back to the sample B, which is synthesis from the hydrothermal approach, you can see the quenching rate is not as much as the microwave synthesis method. Okay, so this is the part showing you a more detailed analysis to seeing the response time. So from the response time, we can conclude that the sample A giving a more higher sensitivity as compared to the sample B, which is taking a longer time to get the reaction. Well, in the visible part, in the UV part, you doesn't observe much of the changing. So it just means that most of the reaction is basically occurs in the surface oxygen defect side. All right. So, and then after that, we have tried to improve our PR sensor to make it a little bit toward the prototype system. So in the prototype system, I get help from one of my PhD student all the time during my postdoc. His name is Chun Hui. Right now, he is working as a Utah lecturer. So in this case, we are trying to alter the PL signal, because PL signal, we need the laser source. Okay, we need the laser source during assembly. But under the adsorbent signal, we don't need the laser source. We can just use the LED light. Okay, so which make our system become more portable. Okay, so but the diagnosis and the detection of the signal now is changing from the PL spectrum quenching rate toward the OAC. Okay, so this is some of the images showing you our sample morphology, which is starting from a zinc oxide nanomer, and we are trying to dope with some of the metal. We call it as an indium doping here. And from the indium doping, we have able to actually circulate and try to modify, okay, the defect of the system. So after that, we are doing a programming using the Arduino, doing a programming to get a signal alarm. So you might come across your mind why we want to set A and also only a 50 ppm of the CO gas, because 50 ppm of CO gas is from the OSHA is actually showing 50 ppm is the minimum level of the CO gas that can kill the human, silent killing, because the CO is something that is odorless, mean you cannot smell it and you cannot detect it. Okay, so that is the reason we come out with the prototype. So this prototype here is actually showing the alarm is starting to ring when we set our offset of the voltage. When it's set to 1.05, is mean that it is aligned to the 50 ppm of the CO gas. So the alarm is starting to actually ringing. Okay, it's starting to ringing. Okay, so this is actually the plot is showing you the sensitivity of 10 ppm of the CO gas. So how we get the differences in terms of the adsorbent is basically we take the OAC for the A minus with the OAC after the CO, which is the last point here. Okay, and then the difference of it is our absolute OAC here. So from here, you can actually observe that when the sample is doping with a 0.4% of the indium, it is actually showing a better response. So, and the next of the application that I want to focus for today is the solar cell. Okay, solar cell is quite important for this recent year, because people is moving to the green technology and trying to reduce the fossil fuel burning, okay, to the environment, okay, and causing the pollution. So in the solar cell, it can classify into 4 different types of the group. One we call it the silicon solar cell, which are most stable and always you can see in the solar farm. Okay, and then you do have the DSSC, the second generation, which is come from the micrograzole group. Okay, by applying some of the dye molecules to it to improve the absorption of the signal. So in the micrograzole's room, if you are free, you can actually go through the Switzerland micrograzole lab. You can actually see the building is actually made up from all of the solar cell with a different kind of panel. Okay, you can just online and search it for that. And the whole building is basically they generate the electricity using their own DSSC. Okay, from the building wall. Okay, and then the third generation is called as OPV. Here is organic photovoltaic, which is the focus in our lab. So why we are still focusing on the OPV is because this material is very flexible and it do have a very good in terms of electron diffusion pathway. And the flexibility of this OPV also make it compatible to most of the bifunctional material. So recently people have tried to invent the PSC, and PSC is a perovskite solar cell. It also somehow is come with the flexibility if you're making a hybrid perovskite solar cell. But the problem is it do have the very high hysteresis issue. Although some of people have come out with the air stable perovskite solar cell, the problem is when you try to fabricate a perovskite solar cell, you still need some of the material like spiro or metal, okay, to coating on top of your perovskite layer. But this material is still humidity dependent. Okay, so at least that you encapsulate all your devices to make the stability become better. Okay, so this is one of the charts from the NREL. Okay, chart they're showing you some of the recent record of the photo conversion efficiency of each type of the solar cell. So if you look from here, so the organic photovoltaic is actually late in 18.2 as compared to those tandem solar cells. It means that you send me just two of the solar cell together, you can always get the double up, okay, the efficiency with 47. But the organic solar cell, although it is still only achieve 18.2, but it have a lot of the plenty of a room for it to make the improvement. Like what we can see from the recent article is showing that the organic solar cell can achieve a higher efficiency if we're trying to improve the stability of the devices, because the main issue for right now is organic compound is not stable yet. So how we are going to improve the stability, this is also one of the niche area study in our lab as well. So, and also we have also looking at the organic solar is starting to move toward the commercialized path as well. So the benefit of the organic solar cell, you can look at it as what I mentioned, is because of the flexibility, it can easily to compatible to the bifunctional application. Okay. So the next one is roughly move on to a little bit concept about the solar cell. So in the organic solar cell, this is also the part that we focus for today. So there is a two part of the organic solar cell. One is a conventional, another one is a inverted. What is the difference between conventional and inverted? Is only the design. Okay, it's only the design of the solar cell. If you look at the conventional, you have a PET, ITO, you have a PWSS, the whole transporting layer is actually at the bottom. And then you have your active materials, okay? And then you have your transporting material and you have the AL. But for the inverted part, your electron transporting layer is basically at the bottom part. So when the light is shining, the light is actually shining from this side. Okay, but for conventional, your light is shining from the top. Okay, so the device structure of the organic solar cell, okay, normally we need to control thickness, which is very thin, is up to less than the 150 nanometer. Okay, because we want to make sure our TEC and the cathode part here, the light is able to penetrate through it and absorbed by the active layer here. Okay, the anode here is stand for the whole collecting layer, while the cathode here is stand for the electron collecting layer. The ETL is a short form for our electron transporting layer, and this is the part that we are putting your nanomaterial here. Okay, and then you have an active layer here. The active layer for the organic solar cell is normally comprised of two kind of components. The first one is a electron donor polymer. Okay, and another one is the electron acceptor, which are made up from the fluorine derivative. Okay, some people will use a low band gap material, but low band gap material sometimes it have a stability issue and they are sensitive to the air. Okay, you need to have a very well controlled condition, okay, to fabricate your devices. So the HCl here is stand for the whole transporting layer lah. So the whole transporting layer is always used to facilitate the whole migration to the anode part. Okay, so and this is some of the concept that appear in the organic solar cell. So we can actually put it into the six step, okay, during the process of the photoabsorption. So the first, the light will actually absorb by the part of the active layer, which is this layer. Okay, the light will absorb by this layer and it will absorb by the donor polymer. So the donor polymer will undergo the exciton generation in the donor polymer, the HOMO and the LUMO, and then the electron from the HOMO side will excite to the LUMO side and undergo the dissociation in the interface between your donor and the acceptor. The acceptor here is the stand for the PCBM, which is your fluorine electron acceptor. Okay, so once your exciton is able to dissociate from the interface, which is in this interface, so the electron will later, okay, transfer to the electron transporting layer. So this is based on the structure of the inverted organic solar cell. So once the electron is transfer to the electron transporting layer, it will go through to your charge collection. Okay, charge collection, which appear in your cathode part. Okay, while the hole that is remain in your donor polymer will later migrating to the anode. So this is what we call it as the charge separations occurs in the organic solar cell. Okay, and the electron will always is the charge carrier, okay, in our part. So how we are going to test our devices for the solar cell? We can actually test it for a common characterization. We call it as a JV characterization under the standard 1.5 mg the filter. Okay, so you can actually get the JV curve. J is stand for the current density and V is stand for the voltage. And then we also evaluate the field factor, which is respond to the photoconversion efficiency ratio toward the changing of the current density toward the voltage. So the squarer is your field factor, the better is your solar cell performance. So this is a general curve that you can always get it from the under the light condition, under when you expose your material with the solar system. Okay, the second testing that we conduct is called as the under the dark system. So when under the dark system mean you no need to turn on any of the light source. Okay, you don't need to turn on any of the light source. Why we want to conduct the system under the dark environment is because we want to study whether there is a linkage current appears inside your devices. So in here, we will study the RS and also the RSH. So for one of the solar cell with the best performance, they will always have the shift resistance, which is very low. So if you look at this diagram here, so if you want to the solar cell have a good response, it means that you want to further increase the complete circuit here. Okay, you want to further increase the complete circuit here. So if you have a very low resistance here, it means that you can allow more of the current to allow to go through it. Okay, if your RSH here is very high, means you will prevent the linkage current to go through the short pathway. Okay, so for a the poor devices, always they have the low RSH and high RS, mean the current will just going to the short pathway. Okay, so and this current we call it as a linkage current, the current that is just pass through in your ETL. It might be recombined back to your active material later on. Okay, so this will come to a more detailed discussion like the germinal recombination or biomolecular recombination occur in your system. So other than that, we also are doing some of the very important tests. We call it as the IPCE test. IPCE stands for the incident photocurrent conversion efficiency. It means how much of the photon that you absorb is able to convert to the electricity. Okay, from here we can evaluate that in which kind of wavelength that your sample is sensitive to the absorption and able to convert the electrical signal. So for the active material that using in our lab is P2H and PCBM. So P2H is always have a very good absorption in the 500, okay, which is in the visible region. So that's why here we are plotting a curve something like this is because our absorption is actually occurs from 500 to 900. Okay, and this is the part where is our exciton generation is occur and convert it to the free charge carrier. Okay, so and some of the scientists in our lab also we are doing an impedance analysis to study the charge transfer phenomenon in the solar cell. So for a good solar cell like organic solar cell, always you have a two semi-loop because you have a two interface. If you are working on the DSSC because you have another interface for the die layer, so maybe in this case you will have a three loop, which is actually showing you another interface is come from the electrolyte system. Okay, so now let's move on to the two loop, which is about the Opv structure. So in the Opv structure, the first loop is actually referring to the interface of bulk recombination of the system. And the second larger loop is actually showing the charge transfer mechanism. So for good solar cell, always we want to have a smaller semicircle because smaller semicircle is mean that you have a smaller resistance, okay, smaller resistance, and then you can actually have a more charge density, okay, in one of the solar devices. So in my group, we have actually split up few of the students to the specific project. So one of my students Aaron Hong is actually working in the inverted organic solar cell, and recently he have come out with a quite good result, with a potential result when he trying to modify the active material with the two-dimensional material and also method of two-dimensional material is able to improve the power conversion efficiency to 65% from the original. If you look at the green line is the one without modification. Well, we modify it, we can look that squareness or curve now is become more squareness, and the PCE has been improved 65%, which is from 1.31 to about 2.16 of the PCE. So this also including with the fill factor improvement from a 37% to the 50%. Why the improvement is too so high is because when we adding some of the metal halide particle into the one-dimensional nanowire, we are able to undergo the surface passivations toward the oxide layer in our organic compound. So this is able to improve the stability of the devices as well. So this thing also has been proved from using a photopaper to measure the conductivity of the sample. By just measuring the conductivity in the photoactive material, we found out that the conductivity of the sample is also increasing, okay, which is from 0.003 to 0.008. Okay, so this is actually the FISM images from the nanowire that we synthesis from our lab. So this is some of the previous study is done by my student Aaron Hong as well during his master study. So during a master study, we are also modify and improve the stability of the devices of the original PHH PCBM sample by doping with the metals 0.6 of metal, which is the indium sulfide here. So we have actually undergo a few of the analysis like the FM analysis to study the surface roughness. We found that the higher is the surface roughness, okay, the better is the contact, okay, between your whole transporting layer toward your active material as well as between the infiltrations of your PHH PCBM toward your zinc oxide nanoroid. Okay, on the right hand side of the images, okay, so we are doing something about the Kpfm analysis. So this Kpfm analysis is for us to study the wall functional system. From the result, we found out that after the incorporation, there is a tree interface of the study, which you can see from the brightness of the system, and you will find out that the Fermi level of the method of PCBM right now is actually shifting upward. Same thing is going to the Fermi level of the P3 HG is actually shifting downward. So this is actually making the offset of the band gap is become smaller. So when the offset of the donor and the acceptor is become smaller, so this pathway is able to lead to a more efficient charge transport system in our IOSC, because we get a better result lah. So if you look at the device table here, so we get a better result for 0.6 with 2.96 as compared to the pristine 2.5 by improvement of the 80%. So other than that, we also put this sample into the outdoor analysis. Mean we encapsulate our sample and then we test under the outdoor analysis for aiming to study the stability of the devices. And then we have test condition under the cloudy and sunny and also under the control system, which is at AM1.5G. So we have figured out that after we have incorporated our system with the metal halide or metal sulfate, so the stability of the devices actually show a very good stability as compared to those without doing any of the modification. So same thing, we are also using a Raman analysis to prove, okay, how our indium is able to improve the crystallinity and also the charge density of the electron from the CCC asymmetric bond here. So it is found out that the sample with 0.6 dopant showing a higher intensity, which is proving that the higher pi delocalized electron is figured in the C double bond C as compared to the pristine sample, which should give you a very low intensities of the images. Okay, so this one is one of the diagram that we are trying to prove our material is really able to sense the light. Even though we are not giving a very strong solar light, although it's under the cloudy conditions or under the LED light or normal white light, our device is able to respond it. So we're connecting our sample in the parallel connection and also a series connection. So here is one of the short clip video showing you. So when we are exposed under the environment, you can see there is some of the voltage and current disappear. But when you're trying to close it, so there is no current is actually generated. Okay. So after that, we have trying to expose our sample with a different kind of light. So this one is with the white light. So you observe that the signal is changing. So after that, we are, let me accelerate the video. So after that, we are trying to lowering a power again. So you will see the value is changing again. And then we change to the red light, okay? The light with the lower power, so you can see the value is decreasing. So this what is mean here is it is mean that our sample is actually sensitive and give response to different kind of the power and is able to harvest the light, okay, to form the energy. So the solar energy is only harvest the light, okay, it's harvest the light and then turn into the usable energy. But how about how we are going to store this energy? Okay, for storing the energy, there is a two common application people is normally work on it. Is one is a battery, another one is a supercapacitor. Okay, so for the battery is they are suffering with the very low power density, okay, but they do have a very good in terms of energy density. So it come toward to the discovery of the supercapacitor because people is trying to get a better energy density and also the better power density. So our group is also now starting to work on in the supercapacitor. And for the supercapacitors, they are always focusing in the Regen plot by looking at the energy density and the power density. So for one good devices, we must always increasing the energy density and power density. Okay, so there is a few of the application of supercapacitor in the current stage is something like people is already applied to the electrical technology buses in the Shanghai, and some of them are using in the UPS, and also the Mazda company, the automobile company, starting to use the supercapacitor as a fast braking system. Okay, so this is a concept that using in the supercapacitor, there is actually a three type, but today we will only looking at the two type. One is the EDLC, electrical double layer. Another one is a pseudocapacitor. So EDLC is working based on the mechanism of the ion adsorption and desorption, while the pseudocapacitor is working on the redox reaction, which there is a reaction of the changing of the ionizations stage in your active material. Okay, so for the material commonly used in the EDLC is the activated carbon, which one having a very high surface area, and this is actually the graphite aerogel system, which is very light. Okay, you can balance just using a spine of the plant. Okay, while the pseudocapacitor, the active material normally people using is more toward the transitions metal oxide. Okay, because we are going to altering the ionization's energy, okay, during the indications and also the indication process. Okay, so this is how we are going to test the supercapacitor. So supercapacitors performance can be tested using the electrochemical property. So the top images, both of these is actually testing from cyclic voltammetric measurement, and the bottom is actually the galvanostatic measurement. Okay, so for the cyclic voltammetric measurements, the EDLC will always give you a perfect squareness because here is the adsorption and the bottom here is the desorption. Okay, well, when you're looking for the pseudocapacitor, we will see some of the oxidation peak and the reduction peak caused by the charge transfer, okay, from the electrolyte toward your active material. Okay, same thing is moving on to the galvanostatic measurement charging discharge. So for this part is the charging and this part is the discharge, and the pseudo peak will actually appear here for the pseudocapacitor, and they will undergo the discharging process. Okay, so here is some of the current study and design of the flexible supercapacitor. So same thing to our lab, we're also working on the flexible supercap by putting our material on top of the fabric called as a carbon cloth, and also the transparent electrode and also the electrode made by ourselves. Okay, so the first one is actually the stretchable supercapacitor. Although you stretch it, it doesn't affect, okay, to the energy storage inside the devices. And and to behave like a power supply. Okay, second one is a bendable, okay, bendable, and then the third one is a hearable. So something like that. After you cut your devices, so you just using a cutting tab or using a solution, so your device will actually uh, return back to its original state. And when you do the connection, we'll find out that it still can light out the light bulb. Okay, and the last one will crumb. Okay, mean you fought your supercapacitor, it doesn't affect at all. Okay, so this is one of the project done by my master student Amalini. So he's focusing is more toward the metal oxide based flexible supercapacitor. So he's one working on the manganese oxide and trying to use different kind of the metal dopant to altering the physical and optical property, physical and electrical property of the material, and study how is the electrical chemical performance can be changes. So from here, he just found out that when he doped with some of the metal, which is a lithium, into the manganese oxide, okay, into the manganese oxide, it will actually affecting the lattice distortion and expansions to the MnO2 alpha system. So when the system is stopped with the 2 millimolar of the lithium MnO2, so it actually figured out that the peak shift to the higher value, which is mean, okay, in the XRD, okay, which is mean there is a lattice constraint and causing a lattice distortion into the system. So when the lattice distortion in the system, it will actually provide a more larger tunnel for the electrolyte to intercalate to it. Okay, so it provide a better specific capacitance efficiency. So other than that, we're also doing some of the Raman analysis to study the crystalline structure and to study the molecular structure of our MnO2 system. Okay, so it actually observed that after he doped with the 2 millimolar, the optimum of the dopant material, okay, the FWHM of the system and also Raman shift is shifted to the larger angle. So which is mean the bond length of the Mn to the O is become shorter, mean it is become a more well crystalline, and then the tunnels in between them will become increasing. Okay, so this part is actually the device performance of the our flexible supercapacitor. From the device performance is proof that 2 millimolar of the lithium MnO2 is showing a better devices. Although we try to ramp the governor static cyclic charge discharge, so we actually observed that 0.2 is giving us a higher specific capacitance with the record of 72.8 farad per gram at just a very small amount of current applied, which is 0.2 ampere per gram. So after then that, so we are able to prove that by doping the lithium dop MnO2 into the lithium dop into the MnO2 nanostructure, we are able to improve the active surface area and improve the conductivity of the system, as shown from this 4.4 curve. And this process is able to increase the charge density of the system and the ionic transport pathway. Thus, we can get a better devices in terms of the specific capacitance. So here is some of the future perspective of the supercapacitor, and it is the first one is a fiber supercapacitor is currently working on it. So we are collaborating with a group, okay, for this part. And we do have the aerogel supercapacitor that we work with the UKM right now by producing the aerogel from the graphite material. So there is also some people is working at the textile supercapacitor by casting, okay, your supercapacitor in the carbon cloth, like what my student doing here. So it's casting in the carbon cloth and try to connect it to light up the LED bulb. Okay, so and then there is a mimicking between a supercapacitor with a nano generator, which comes from a piezo generator. So you can use the piezoelectric to generate the electricity and store in the supercapacitor for some of the functional materials usage. Okay, so for us to feel all of these combinations of the technology, so the transparent conducting material is come very important. So most of the people will use a solid material like the ITO. So ITO having a very high transparency, but it do have a high conductivity, but always is something like it have a defect and scratching that affecting to the device performance. So people is now working to the flexible device conducting material, like applying a graphene which have about 100 ohm to 90%, And they're also doing a carbon nanotube, metal nanowire, or conducting polymers to trying to altering the transparency and also conductivity of the material to be used in the flexible devices. So our group have collaborated with the UKM group, okay, the Dr. Lau, to actually making a flexible and stretchable film from the silver nanowire produced from the flow synthesis. So from here, this is images from the FISM of the silver nanowire. And then we have proof that the current density of the nanowire is get improving after we apply a bias for 0.2. The drift current of the silver nanowire is getting improved from 0.053 nanoampere to 0.093. This analysis is conducted using a Kpfm, okay, which is the conducting AFM. Okay, it is also available in our UPM lab right now. So if you are interested to do it, you can always approach to the Dr. Nana to book the appointment for it. Okay, so and then this diagram is actually showing some of the current and conductivity changing against the sample bias. So we have actually observed that when the sample is applying some of the bias, the current is changing. This is mean that our silver nanowire is get response, okay, to the electricity changes. So right now we also have to taking spraying this silver nanowire to some of our contact material, okay, to make it as a contact for certain of the devices. So other than that, my new student, master student, also working on the flexible and stretchable film in the multi-layer graphene based electrode. So he's right now is starting to work and try to blend the nanostructure into the graphene layer in hope to improve the conductivity. Up to now, we have managed to get the conductivity on the graphene flex film, which is up to 40 ohm. But however, this graphene flex film is not transparent. So we will use it to replace it to the carbon cloth that we always purchase it in the textile supercapacitor. So this is one of the images showing you here is this is the original size. So we are able to stretch our graphene electrode, okay, graphene electrode to the stretching angle, and later he will return back to its original stage, okay, and the conductivity is doesn't change much, okay. So for the further discussion about this, I will include to you if you can approach me, okay. So and lately we also are working on the flexible and stretchable latex based electrode by using a isomer of the latex. So we are embedding with the silver nanowire, so to make a transparent electrode. Our hoping is we are going to make it for the hewable devices. So this is one of the images showing you some of the impact original and after stretching. So this part we will actually use it for our application in the e-skin sensor and supercapacitor. So the last part of today's talk for the device is the bifunctional devices. So we also utilize our sample into the different kind of the multifunctions. So in this case, we have a blending between the MnO2 nanowire with the MOS2 nanosheet. And this result is actually conducted by one of my undergraduate students. Yeah? So we are combining these two nanostructure and observe from the Raman that we are able to detect, okay, the multi-layer and the single layer of the MOS2 and also the symmetrical bonding of the MnO2. So other than that, we also use the XRD to detect the structural property of it. So from the electrochemical glucose sensor, we found out that the MnO2 is respond to the different concentration of glucose, while the MOS2 itself, the layer doesn't give the response. And then when we try to combining between the MnO2 and the MOS2, we found out that the reaction is become more reactive, in which we get the oxidation and the reduction peak of the glucose detection. So after that, we try to improve the potential that we apply to the system and fix the glucose concentration. At this level, we found out that MnO2 has something like saturated. Okay, the peak is starting to saturate. It does mean that it doesn't give any response to the glucose detection. Same thing to the MLS2, it doesn't give any reaction, while the MnO2 and the MLS2 is giving a better reaction. Okay, when we are trying to apply to the different potential. So after that, we have running up some of the empirimetric analysis and figure out that by embedding the MOS2 and the MLO2 together, we are able to improve the glucose detections, okay, from the 0 millimolar up to the 12.5 millimolar with the voltage offset of 0.55 volt. Okay, so the mechanistic behind this is because we are expecting that the MLO2 is just H as the absorption region, okay, which is undergo the reactions. So the glucose will change to the gluconolactone. Okay, well, the MOS2 is just a surface to improve, okay, to improve the absorption without doing any of the reaction. That's why you cannot see any response in the CV as well as the empirometric. Well, you try to combine both of the material together, so the MnO2 will undergo the reaction, while your MOS2 will improve the surface absorption. So this process is able to make use your materials to become a very good glucose sensor. So the same material as well, we are testing in the supercapacitor. So we have found out that when we testing to the supercapacitor, the devices of the MOSU is not only can be had for the glucose sensor, but it can also use for the energy storage devices. Okay, because when there is a reduction in the oxidation process, there is a charge carrier transfer. So this energy is able to store inside our emerging material. Okay, and the improvement from the MOS2 to the MnO2 is showing a 12-fold increment in terms of the energy storing inside the capacitance. Okay, so the next of the bifunctional devices is that we have working and collaborate with the Monash University with the Dr. Lin function is we working on the bimetallic metal system. So in the bimetallic system, we are using the drilling method, okay, to combine the AU and the AG together. So from here, we have figured out that when we try to increase the concentrations of AG to diffuse into the AU domain, so this AG is giving a very nice diffusion layer. We'll be doing a simulation using the embedded atom method. So this embedded method, the simulation we conduct using a molecular dynamics simulation, and we have found out that the AG have a possibility to incorporate to the AU evenly. Okay, so after that, we have also working on some of the detection of AG by visualize using a stamp. So the bottom result here is actually showing you some of the E field, electrical field density of the devices when we conduct using the FEM, finite element method. So from the finite element method, so we figure out that the sample when we are incorporated with the AG by metallic nanoparticle, we found out that the electrical field is not only improved in the outside, but also improved in the inside of the system. Okay, so this is a further proof that when we mimicking the AG and the AU together, we can improve the electrical field of the system. And after that, we are using this material for the dye detection, SERS, and also a PEC application. From a PEC application, we have observed that there is an improvement of 80% of the current density when it's compared back to the baseline of the AGAU toward the one we do in the bimetallic system. Sending for the dye detection, so the dye detection also showing that 0.25 AGAU is giving us a very good detection limit from the 10 milligram per liter up to small volume, which is 0.01 milligram per liters. Okay, so now I give some of the review for the current application. Like I said just now, supercapacitor is not only limited to the laboratory scale up to now, but they're also starting to apply to the industrial view like the Mazda, who are using it for the fast charging and the discharge for the regenerative braking system. Okay, so there is a few of the future application is currently working by the people like the smart fabric. So when you wear the smart fabric, you can actually charging your phone easily, and they also try to combine the solar cell together with a supercapacitor as reported by the University of Guangzhou. Okay, so there is some of the take-home message for today's topic is first we need to understand very well the nano regime is very critical to bring forward to the eventual commercialization, and material design is kind of very important for you to produce a high performance optoelectronic device if you are able to tune the electrical and optical property of the material based on the specific parameter that you want to study. Okay, there is a future study of the devices right now is people is more favorable to learn about the device that you are able to stretch, heal, bend, and fold it and it doesn't affect to the device performance. So the next generations of the supercapacitor will be the self-charging flexible supercapacitor. So by using this chart, I would like to analyze a few of the members in the advanced material device laboratory, especially to my graduate, postgraduate student, and also my collaborate and UPM for actually giving me funding, okay, to done and complete few of the works, and also the UKM, Monash, Utah, NTU, Korea, Chombo University, Princeton, my collaborator university, for always giving us the support, yeah, especially in the simulation project, and as well as some of the device analysis that we couldn't conduct in our small scale laboratory. And last but not least, I would like to thanks to the MOHI, Ministry of Higher Education, for provide us some of the FRGS funding to support our research. So if you do have any question, you can always contact me in this email and line. Okay, so by using this, I would like to take the opportunity to give the vacancy. There's a 3 vacancy right now for the master research. So we have a 3 project, one master by research in the sensor part for the ammonia sensor, and we do have another slot for the master in quantum dot, and the last one is the master student for hybrid perovskite solar cell. So right now we are open for the vacancy, and if you have any friend or any student who are interested, you can always ask them to approach us from this contact. Okay, thank you very much for today. Thank you.
Thank you, Dr. Tan, for the interesting presentations on nanomaterials. I'm Dr. Chan, so I'm replacing Dr. Hisham for the Q&A sections because at Dr. Hisham place, there's some renovations is going on, so it's quite noisy. So now is basically the Q&A sections. So if any of you have any questions, feel free to ask Dr. Tan. So any questions from the floor? No questions?
Maybe I can ask.
Oh, okay. Dr. Hisham, you can ask.
Sorry, it's gone quieter now, so I can ask questions. You had this criteria that you had earlier about what to do with respect to this nano materials and nano device. Now, how much control do you have on the structures that you're going to construct or manufacture? And is it by chance? Things like, for example, you had the earlier slide with the nano-flower structure kind of thing. These are they appear by chance, or is there some mechanism actually involved in this particular manufacturing of these nanomaterials?
Okay, thanks for the Dr. Hisham question. It's a very nice question. Okay, for the nanostructures design and architecture, for sure we have a theory behind it. So basically for those who are in the material science, okay, so if they want to something like altering one of the structure, for example, for the nanoparticle to the nanostructure, so we can using a different kind of approach. So maybe you can actually changing the easier way is you changing a surfactant and the ligand. Okay, so for example, if I have a type of the surfactant, okay, surfactant is something that we can control how our nanostructure is getting to grow in which kind of the direction. Okay, so the common surfactant that we are using is, for example, like PVP and CTAB. Okay, so this is two common thing lah. So like PVP is always, if you're using a PVP, so this PVP will bind to the H side of your precursor, being your raw material. Okay, when they are keeping to the H side of your sample, so what will happen is your nanostructure is just tend to able to grow vertically, right, Dr. Hisham? So you will actually get a nanostructure, something like the bottom images here. Okay, the dot zinc oxide nanorod. Okay, if let's say we want to control some of the sample to the spherical light structure, okay, spherical light structure, so most often they are using a CTAB, because CTAB they will actually cap it, okay, depend on what kind of material using as well. So but mostly like the silver metallic structure, CTAB they will actually cap it in the 100 plane. Okay, when they keep it in the 100 plane, okay, the solid state plane, so what will happen, your material will go spherically, okay, rather than into a 3D dimension. Okay, am I answer your question, Dr. Hisham? But always one analysis is not enough for us to prove out this mechanism. So this mechanism, always we need to use a different kind of analysis method. For example, okay, we need to prove it not only using the something like a Kpfm analysis is just for you to prove the morphology, but you can also prove it sometimes. Okay, we need to use the FTIR, we need to use the XPS, okay, the X-ray photoelectron spectroscopy, to prove how is the transition to the electrons that involved in the chemical reactions during the synthesis approach. Yeah, from there we can actually propose out the suitable mechanism why this nanostructure will form. But ideally is always people is like us, we are already knowing like PVP, CTAB, a common ligand or common surfactant, they are always bind to which side. So from there you can actually know how will going on to the output of the nanostructure will form in the final product. Okay, so this is the first approach using experimental issue, okay, experimental method. Second method that you can use it is using simulation method. Okay, you can use the molecular dynamic simulation, okay, to study the self diffusion and impurity diffusion of the certain of doping material if you doesn't have the ligand. So like what I'm showing you just now, okay, in the bimetallic system. Okay, for example, this bimetallic system. Yeah, okay, this bimetallic system. In the bimetallic system, how we are going to prove the mechanism whether the silver is coating outside of our AU nanoparticle, or it is just scattering around, or it is not exist inside our bimetallic AgAU. So in this case, we will actually use a simulation to study the self-diffusion property and impurity diffusion property of the materials. So from here, we will control how many ratios of the mole ratio of our Ag and Au, and then we will run the simulation, and this is actually the output. So from the output, you have figured out that under this ratio, so the silver can be evenly distributed, okay, into, okay, diffuse into our Au host material. Am I answer your question, Dr. Hisham?
Yeah, okay, thank you.
You're welcome.
Dr. Chan,
Um,
I have a question.
yeah, please.
Yes,
Uh,
Nana.
from your slide, which is you show about the two type of the conventional and inverted device. So how we attack the positive and negative, the cathode and anode? Like the
May I repeat, Nana, Dr. Marciana, question is how we are going to connect our cathode and anode, is it?
Yep.
Okay, so let's me back to the slide. I think Dr. Marciana is talking about this slide. Okay, so for this slide, okay, this slide is actually, just a moment, yeah. Okay, this slide is actually referring only to the organic solar cells, yeah. So in the organic solar cells, we can have the conventional and the inverted type. So how we are going to connect this one is mostly we are using a crocodile clip. Okay, crocodile clip during a testing. So during a testing, we have one crocodile clip. Actually, this is a layer structure that we are drawing, but the actual structure is actually look like this. Okay, it look like this. Okay, so when during our synthesis, so you can see I hope Dr. Masana can see my cursor is moving now. So you can see actually the silver color here. Am I right? The silver color here is basically is our cathode material. Okay, and this part is our anode. Okay, so when during the fabrication we will etch away, okay, we will etch away the layer of the photoactive material, zinc oxide, and it will left behind only the FTO. So the transparent part here is actually the FTO. Okay, and this part is our silver contact, which is our cathode. This is our anode. So during a testing, we will put our crocodile clip like this. Okay, so we will put one at the cathode and another one in the anode. So the part that we do the testing is involved is only this circle. This circle we call it as the active area. You can control it. Okay, so in our case, we want to make our calculation become simple, so we always control in 1 centimeter square lah. Yeah.
All right. So when you put the clip at the clear area, does it scratch? Does it give the effect to the measurement?
Normally for a good crocodile clip, it doesn't give the effect lah. A good crocodile clip lah. If you're using some crocodile clip as simple like this, yes, it will scratch your anode. If you repeat your measurement for a few times, so this will affect to the JAC and VOC of the devices. So what currently is using in the testing, rather than using a crocodile clip, so we will actually putting this sample direct to the sample holder. So they will just using a pin to on touch to the anode and cathode. Is it just like a pin? You put a pin here, you put a pin here, and then you can do a series of the measurement in one time.
All right, okay. And then you also mentioned about the hydrophilic hydrophobic, and you know that I'm synthesis quantum dots in physics.
Yes.
And but then we try to combine with the other nanostructure and then let it dry. So do you think that from your opinion, does it still consider as the hydrophilic after we hybrid with another nanostructure?
For my opinion, I will say that it depends. Yeah, it depends on the materials. Okay, so some material after it coating with the QDS, so it could change the weathability, but some not. It depends on how is the surface coverage of your QDS on top of the nanostructure as well. So this is what I can say. But later, we also need to observe from the result from the weathability, which is using a contact angle to confirm this. Yeah, something like quantum dot. But we have one recent paper, okay, that we published in the Journal Materials Technology, and we are actually adding a fingernail. Dr. Nana, I think it's same field with you. So what we're doing is we're taking a fingernail, okay, and then we adding inside the quantum dot casting G C3 and 4, okay, and very obviously when we adding a carbon QDS, okay, when we adding a carbon QDS, the wettability of the sample is basically increasing, so that it help us a lot in the Cu metal ion detection. Yeah, but this thing I couldn't give you a direct answer for that. Is because it really depends on how is compatible between this quantum carbon dot to your host material, and how evenly is the distribution of your carbon quantum dot that is casting on top of the host atom. Yeah.
All right, thank you.
Yeah, welcome, Nana.
Right. So any more questions from the floor?
I have one question, Dr. Chan.
Right. Yeah, please.
Dr. Tan, did you optimize the parameter for your nanostructure? And then my second question, how did you? Okay, so that means you will optimize the parameter for the nanostructure first, and then how did you control the stability of your solar cell? Because you
Okay.
know the organic material is not stable, right?
Yes.
So yeah, because we need to synthesize the nanostructure first, right?
Yes.
So I want to know how did you control, and then how did you integrate your nanostructure with the your device? Yeah, that is my question.
Okay, so let me try to summarize a little bit Adila question. So Dr. Adila question. So the first question is it am I optimized the nanostructure? Yes, we have optimized the nanostructure based on the application that we want to apply. For example, okay, in terms of the solar cell, because Dr. Adila is asking me in terms of the solar cell application. So let's have a look for one of the slide, maybe this slide, which is already published. Okay, so for example, for this one, so for the nanostructures, whether we have modified it. So for example, for this sample, our nanostructure is using under the zinc oxide nanorod. Okay, we're using under the electron transporting layer. So what is the part that we want to optimize is actually just the conductivity and thickness of the electron transporting layer. So we will do a trying, okay, not the trying, the experimental, okay, by always we taking a 10 times, yeah, at least a 10 time for one of the devices, and then we will actually alter different thickness of the zinc oxide nanorod. Actually, this is our first stage before we come to this finding. So we will actually try to study how the thickness of the zinc oxide nanorod will affect to the consistent P2H and PCBM. After that, we will get a optimum thickness, and this thickness is actually with reference to the charge transport rate of the electron transport from the PCBM toward our anode. Okay, because sometimes the longer is your zinc oxide nanorod, it doesn't mean better, because it will actually preserve more site for the recombination to occur. Okay, because zinc oxide nanorod, everyone know, is a defect-rich materials. Okay, the longer you grow it, actually the more the defect you supply to the solar cell system. Okay, so we are actually control up to the optimal. This is how we control the zinc oxide nanorod in our organic solar cell. And after that, we will do the modification. Second part is the stability of our active material. So in the organic solar cell, everyone is know that organic material is not stable, right? It is very hygroscopic. When you expose to the air, it's very fast to get high rise. So what will happen is we're trying to modify the molecular structure of our polymer by adding some of the indium sulfate in this study. So in this study, we are doing a control study, okay, by altering the doping concentration from 0.4 to 6, 8, 10. So maybe you'll come to the mind why we select this range. Before we doing the analysis for the experimental, actually we will do a simulation study. So we will run out the simulation to see which kind of the percentage is able to compatible to our polymer structure. So after that, we will actually shorten up our study range. Okay, we'll shorten out narrow out our study range, and then we will trying from here to optimize how good is the incorporation of our indium sulfate into the P2H. So what is the analysis that we're looking for on this point is because for the stability of the organic solar cell, so we were looking on how long lasting is our device is able to attend to the certain PCE. This is the first thing. Second one, is the reason how stability can be remained. So stability can be remained in organic solar cell is nothing avoid from your work function. So that's why we have the work function analysis using a Kelvin probe microscope, okay, to study the energy offset. So like for example, when we dope our sample with the 0.2, 0.4, 0.6, 8, and 10, so we will run a series of the Kpfm analysis for all of the sample. But today we are just showing you the part of the optimized sample. So from here, we can actually look how is the shifting of the energy offset in the modified sample. And from there, we can actually propose up the mechanism occurs in the charge transfer step. So lastly is the output. Okay, is the output. So how we want to confidence the reader. Okay, our sample is really have a good stability. So we will do a stability testing under the different conditions like the cloudy condition, sunny condition, or we will test our device for few months time. Okay, to see how is the degradations occurs in this OPV. Okay, am I answer your questions, did
Yes. And then how did you integrate your? So that means you fabricate the nanostructure with the. Oh, okay. So I understand. So that means you modify your active layer.
Yeah. So
Okay.
in this case, we modify the active layer. Our nanostructure is just the electron transporting layer. We do have doing that study, but not included here because that is the first study that we are putting our zinc oxide nanorod. So for example, if you look from here, okay, so this is our device structure. Okay, so we are actually using our nanomaterial zinc oxide, just electron transporting layer. So when we modify our photoactive layer, we doesn't change the zinc oxide nanorod because zinc oxide nanorod is already optimized to certain thickness. Okay, well, what we do the modifications is only on the photoactive layer, and what is the problem that we want to cope with is a stability issue.
All right. Okay. Thank you, Cynthia.
Yes, welcome, Dr.
Right.
Ila.
All right. I think that's all for talks today because we have
Yeah.
exceeded the time. It's
Yes.
already 4:30. So if you all have further questions, maybe you all can directly email Dr. Tan, or maybe you can WhatsApp her lah, for further questions. But for sections today, I think we will stop here. So let us thanks Dr. Tan again for the interesting presentations. Thank you, Dr. Tan.
Okay, thank you, Dr. Chan and Dr. Hisham.
Yeah. So now
Thank you.
I pass back to Dr. Hisham. Right, Dr. Hisham, please.
Okay, I'll just stop the recording. And then if you want to chat, you can still chat. Okay, let me stop the recording now.